Alright, so once we've seen graphs and what they are, we're going to look at some of the uses of graphs and some of the problems that are associated with general graph theory. Alright, so here's one problem that comes up sort of naturally in graph theory. So let's pretend we want to travel and hit certain spots. Like if you're a UPS driver or somebody who's designing the routes for the UPS drivers or FedEx drivers, you want to hit certain spots and certain delivery drop-off points, and you want to find an economical way to do this. So you don't want to do a lot of backtracking. You don't want to, go over the same places that that you've done. If there's two neighbors, you want to hit them fairly close. So the way this is translated into graph theory is by what's called a Hamiltonian path or Hamiltonian circuit. Now a Hamiltonian path, we saw what a path was before. A Hamiltonian path, or Hamilton path, I should say, is a path that hits every vertex once. All right, so if we have a graph, there it is. If we have a graph, let's just say I have a nice complete graph on 4 vertices. I'll call these vertices V1, V2, V3, and V4. Well, a Hamiltonian or Hamilton path would be something like V1, V3, V2, V4. All right, and I'm going to put dashes in here so we can see that. And if you think about this, V1, V3, V2, V4 hits every vertex once and doesn't have any and doesn't repeat here in this case. So it hits every vertex exactly once. Now a Hamilton circuit is a path that starts and ends at the same vertex. So if I were just to take the same thing we started with, V1, V3, V2, V4, and then go back to V1, that would be a Hamilton circuit. All right. And notice that these are not unique. Obviously, in this case, there's a lot of different ways. I could have started at V1, hit all of the vertices, and came back to itself. You could have went this way. You could have went this way. You could have went this way. All right, there's a lot of different ways to do this. So oftentimes there's many different Hamilton paths or Hamilton circuits in a graph, but sometimes there's none. There are graphs which don't have a Hamilton path, that you can't hit every single vertex once, or you can't start and end at the same vertex and things of that nature. All right, so let's take an example of a graph here. And I've drawn this a little bit sloppily, but we can see vertex 1, 2, 3, 4, 5, and 6. I don't know why I labeled them that way, but why the 3 and 4 down here, 1 and 2 up there. But they're labeled the way they want. So let's find a Hamilton path. Now remember, to have a Hamilton path, we need to fall on the vertices all at the same, exactly once. So we need to hit every single vertex once. Now, oftentimes I may ask you to start at a certain place. So here's what we're going to do. We're going to start our Hamilton path at V1. All right? And there are times when I may ask you to end at a certain place as well. Now, this one, it turns out, it forces us if we to do some things in order to get a Hamilton path. So it turns out I always have to, in this case, start at V1 or V2. But if you think about it, you start at V1, you can go down to V5, V3, V4, V6, and then out to V2. So that is one Hamilton path. So going from vertex 1 to 5 to 3 to 4 to 6 to 2. By the way, that's not the only one in this case. You could have gone V1 to V5, V5 to V4, V4 to V3, V6, V2. All right. By the way, there are some certain things you can't do. For instance, if I went from V1 to V5 and now I go to V6, well, now I'm out of luck, because if I go to V2 next, then to get down here, I'd have to go back through Z6. So V6 would have hit twice, which is not okay. Also, if you went to V6 from V5, if you go down to V3, now you can't get to V2 without going through V6. So there are multiple ways of getting the Hamilton path. However, not every single combination works. In this case, if I go from V1 to V5, V5 to, let's do V4, V4 to V3, V3 to V6, V6 to V2, that'll hit every vertex, and it'll hit every vertex exactly once. Now I want you to notice something about this, and the something I want you to notice is that if I was going to find a Hamilton circuit, I couldn't do it. In order to find a Hamilton circuit, you'd have to find a way to trace back up to V1. And the trouble with that is once you've passed V5, you can't use V5 again. So to try to trace up back to V1, it's not going to work. So it turns out here's a Hamilton path for this graph. Hamilton circuit for this graph does not exist. A lot of times we'll just put D and E for does not exist. All right, so let's take another graph, and I've drawn this one. This is a graph known as a tree, but try to find a Hamilton path here. Push pause and see if you can, if one exists. It doesn't matter where you start from, but I want you to, find a Hamilton path. Now, hopefully you've done that and you've tried some things. No, it turns out you may think start at V1 again. Well, after you go to V2, you have a split off. And so if I go from V1 to V2, if I go from V3, I cannot get back to this side of the graph. If I go to V4, I can't get back to this side of the graph. So starting at V1 won't work. So you might try to start at V5, but it turns out the same problem happens when you hit this one. You go to V3, and all of a sudden you can either go to V6 or V2. So you choose one or the other side of the graph. And notice that there's problems with things like this, unless we can circle back around. So in this case, our Hamilton path does not exist. Right? And there are going to be cases where you have graphs where the Hamilton path doesn't exist. We saw a case just a second ago where the Hamilton circuit didn't exist and the Hamilton path did exist. Here, neither the Hamilton path nor the Hamilton circuit exist. You can kind of understand that if a Hamilton path doesn't exist, a Hamilton path doesn't exist, Hamilton circuit is not going to exist as well. All right, because the Hamilton circuit means you would go back to the first one. So you'd have a sort of an embedded Hamilton path inside there. Okay. All right, so what we've seen is we saw two examples of graphs where a Hamilton path exists, Hamilton path doesn't exist, Hamilton circuit exists. We saw when I introduced, there was a graph where both Hamilton paths and Hamilton circuits exist. And so a lot of times it's hard to check and find out whether Hamilton paths and Hamilton circuits exist. And it turns out this is a big unknown problem. There's no theorem that exists for all graphs to know if they have a Hamilton path or a Hamilton circuit. There's no nice singular theorem that encompasses every single graph. Turns out there's a lot of graphs, and you can create things with Hamilton paths and with Hamilton circuits, and things without. But there's no one rule that takes care of everything. However, there are certain classes, certain types of graphs that will always have Hamilton paths and Hamilton circuits. And I mentioned one of these earlier in this section, but I didn't go over it very, very thoroughly. So I'm going to look at it now. All right, so we're going to look at two types of graphs. One's called circulant graphs, or some people will call circular graphs. And the other is called complete graphs. We'll see that in just a second. I mentioned complete graphs earlier. We'll go into that in just a second. But let's start out with circulant graphs, or circular graphs, some people would say. Okay? So a circulant graph is where every vertex has degree 2. All right? Oftentimes, circulant graphs are denoted C sub n, where n is the number of vertices in the graph. So let me just think. Let's take a 5, C sub 5. 2, 3, 4, 5. The easiest way to draw a circulant graph is to just draw it as sort of the outside perimeter where we go point vertex to vertex, and we travel along edges. Okay, so C5 looks like this. Notice that if I draw, this is called a circulant graph because, if we drew this, we could make it kind of look like a circle. All right, and it does go in a sort of circulant pattern. Okay, it circulates in one sense. So this is the easy way to draw circulant graphs, and it's pretty clear that there's a path, Hamilton path, and a Hamilton circuit by just traveling around the outside edges. Now, I don't want you to think that that's the only way I can draw it, because you could have 5 different points, and you could draw the circulant graph in a very, very different way. Here's another way you could draw it. Okay. And it turns out, obviously, every single vertex, again, has degree 2. If you look at there's 2 edges, 2 points that are connected to every vertex. And I'm claiming anyways, that this graph on the left is actually the same as the graph on the right. So let's take a couple of things. Let's call this vertex 1. I'm just going to actually use the numbers instead of using the V1s. I'll call this vertex 2, 3, 4, and 5. Notice that if I called this vertex 1, well, vertex 1 is connected to 2 and 5. So, this would be 2 and this would be 5. And vertex 5 is connected to vertex 4, so this would have to be a 4. 2 is connected to 3. 3 is connected to 4. So technically, these two graphs are the same, just the one on the right is a different look than the one on the left. All right. Notice they're the same because they have the exact same connections, and then they have the exact same pattern of the vertices. 1 goes to 2, goes to 3, goes to 4, goes to 5. 1 goes to 2, goes to 3, goes to 4, goes to 5, and always back to 1. Okay? Now, it turns out that Hamilton paths, Hamilton circuits aren't too awfully interesting on circulant graphs because really there's only one Hamilton path and one Hamilton circuit from any vertex. For instance, if I started at vertex 1, I'll write the V1. You can either go around clockwise or counterclockwise from the figure on the left. All right, so you can either go V1 to V2 to V3 to V4 to V5, or you could have gone backwards, taken V1, V5, V4, V3, and V2. All right? And these are just, the reverse order of the paths. So, and you could have started at different things, but again, you get the same order regardless of what you do. All right? All right, so here's what I want you guys to do. I want you guys to draw a C6 and a C9. Draw circulant graphs C6 and C9. All right, hopefully you've done that. Push pause on the video and all that kind of stuff. C6, fairly straightforward. 1, 2, 3, 4, 5, 6 points ranged in a circle. That's the easiest way to draw things. C9, we're going to have 9 points, obviously. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, 9 vertices. Oftentimes, again, I call vertices points, and edges, lines sometimes, but you guys know what I'm talking about. So, there you go. All right, so as long as I counted right, it's a fairly straightforward process. And, again, when we talk about Hamilton paths or Hamilton circuits, it's pretty straightforward. Hamilton path, you go all the way around and you stop before you jump to the last one. Circuit, you just jump to the last one. All right, the other type of graphs that come up a lot are called complete graphs. Now, complete graphs are denoted by K sub n. So a complete, we don't want to call it C sub n because that's what the circulant graphs were called. And so we say K sub n. Now, let's draw just K sub 4. K sub 4 is going to have 4 points. And what makes it a complete graph is that every single connection possible is made. All right? So if I take my 4 vertices, each vertex is connected to the other vertices. So each pair of vertices is connected by an edge. And this allows not just for one Hamilton path or one Hamilton circuit, but it turns out because this is complete, any combination of the 4 vertices will yield a Hamilton path. And you can always, because it's complete, you can always go back to the original and make a Hamilton circuit from that. All right, so for instance, let's just make sure we have them all. Let's start at V1. If I went from V1 to V2 to V3 to V4, that would have been a Hamilton path. V1, I could have rearranged anything, any order that I want. So let's switch the last ones. That's another Hamilton path. V1, we'll start at V3. V2, V4, that works. V1, V3, V4, V2, that works. V1, V4, V3, V2, V1, V4, V2, V3. So each one of these, no matter what order we're in, gives me a a Hamilton path, okay? Because we have all of the connections, you can always jump to a next vertex. And just by adding V1 to the end of these, we get the Hamilton circuit, all right? So complete graphs are really, really nice because they allow us to get lots and lots of circuits and lots of paths, Hamilton paths and Hamilton circuits. Circulant graphs are kind of nice because there's one way to go around, all right? So it's forced upon you. Complete graphs are sort of the opposite. You can go around any way you want. So what I want you guys to do is I want you to draw the complete graph K5 and the complete graph K7 and see what those things look like. So push pause on the video, draw those, and see what they look like. All right, this is how I like to draw these. In fact, I might draw them in different colors. Complete graph on 5 vertices. 1, 2, 3, 4, 5. I start by going around the edges. And then go in here. And I think I got them. All right. By the way, here's one way to check. Just check that there's 4 edges. Since we have 5 vertices, the degree of each vertex, if it's connected to all the rest of them, will be connected by 4. So each vertex will have degree 4, all right, because it's connected to all of the other vertices. So since we have 5 vertices, there'll be 4 other vertices each time. So 4, 1, 2, 3, 4, that one's good. 1, 2, 3, 4, that's good. 1, 2, 3, 4, 1, 2, 3, 4. All right, so that makes, that's sort of a check in making sure that you, in fact, made all the connections that you wanted to. K7, I'm going to draw this with a green, I think. Well, same deal. Make all the connections. Sometimes it's a little bit harder when you have higher degrees to make sure that everything is there. So I got 7 vertices. Maybe I'll draw these dots a little bigger too. So to draw the complete graph on 7, go around first. I'm going to take one of these there, 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 there. Take the other there, 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 too. There, 3, 4. All right, I think I have them all. Again, this one you could count by making sure there's 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Oh, I missed something. 1, 2, 3, 4, 5, 6. Good. And I think I have 6 in from every single vertex. Notice that there's a lot of connections in a complete graph of order 7. And you can imagine trying to draw a graph like the complete graph on 50 or the complete graph on 60 vertices. There'd be a lot of lines, and you'd have to space it out. Okay, there are online representations of these, but you see that it is a bit difficult to draw when we get to really high dimensions, or really high numbers of vertices.